we can understand how our universe came to be as one of these sort of drops inside a rapidly expanding universe. But generally, if that's true, there are other universes out there that could be quite different that we'll never know about because the space between us and them is expanding.
Lawrence Krauss is a theoretical physicist and cosmologist. He's focused on issues ranging from the Big Bang to particles. In one of his cosmological papers, Krauss discusses dark energy as a quintessence field. If you think dark energy simply drives the universe's expansion, Krauss's work argues for a more dynamic role of this mysterious force. He's also investigating the puzzling question of why is there more matter than antimatter, or why is there more antimatter than matter? It's the same question. And by doing so offers insights into CP violation. We explore that in this podcast. Often it's assumed that both should be produced in equal amounts at the Big Bang. However, this is clearly not the case since we're here. Why this discrepancy? In other words, why are we here? How is this even possible? We also touch on Dyson thought experiments about gravity and how we can live forever. Also, while neutrinos are often relegated to the role of elusive particles in standard physics curricula, Krauss sees them at the heart of several cosmic processes. We talk about why this is. My name is Kurt Jaimungal, and I have a background in mathematical physics, and I use that to analyze the various theories of everything that are out there, like string theory, like Wolfram's, like what's coming up is Peter White's Euclidean twistor unification. But I also explore consciousness and its role in fundamental law. Due to an ineluctable storm converging on Krauss's location, this interview will be more concise than usual, and we're super keen to expand on it in future episodes. If you have questions for Lawrence Krauss, then leave them below in the format query by writing the word query with a colon, and then your question. This way, when I speak to Krauss again for part 2, all I have to do is look through the comments, search the word query, and then ask your question, citing you either in the description or orally in the episode itself. Enjoy this podcast with Lawrence Krauss. Professor, welcome to Theories of Everything. It's an honor to have you. How are you doing?
It's an honor to be here. I'm doing fine. It's an honor to be here.
Great.
Actually, it's a little tense here. I was just outside preparing for a hurricane that's going to come by here, and so just getting the boat out of the water. And if you look, my Zoom will follow me. Anyway, there's water back there, and anyway, but so far the weather's fine right now, so that's good.
We'll make it a short and sweet podcast. And if you, as an audience member, have questions for part 2, then leave them in the comment section below, because Professor has to go and prep. I've been reading your book. It's a fantastic book. And
Thanks.
In particular, see this subtitle. It says, Unsolved Mysteries of the Cosmos. I think that's particularly apt, because there's this series that I love called Unsolved Mysteries. And this is like the physics version of that.
Well, I think it's always. I'm glad you like it, and one of the reasons the title is there because mysteries are exciting. Some people are afraid of mysteries, but mysteries should be an invitation to everyone, and so unsolved mysteries are really exciting because it's an invitation to everyone to think about how to solve them.
Yeah. So, what does this process of refinement look like for the chapters? Because there are various unsolved problems in physics.
Well, what I wanted to do. Look, I've written a lot of books, and I wanted this in some ways to be a nice follow-up book. The book I wrote, A Universe from Nothing, was sort of at the forefront of cosmology, and then I wrote a book afterwards called The Greatest Story Ever Told So Far, which brought people up to date about the development of what is by far the best scientific theory ever developed by human beings, the Standard Model of particle physics. But I think the next step is to see where we're heading in these fields. And to know where we're heading, it's good to know what we know we don't know. In fact, in England, the title of the book is called The Known Unknowns for that reason.
Which is what you wanted.
Yeah, it allowed me to take those forefront issues, which I know are pushing modern physics and also beyond physics. And those are the areas, and of course the forefront is just at the edge of knowledge, literally. It's where there are questions we have, but we don't know the answers. And I think that's the most exciting thing for people. And I think I wrote at the end of the book, for a young person, when I was young, I read a book that got me excited about physics to realize the questions weren't all answered. Mm-hmm. And so I tried to focus on the most exciting questions. And the neat thing about it, the thing that made it particularly attractive, is that those questions are the same questions that we all have about the universe. How did the universe begin? How will it end? Are we alone in the universe? How did life begin? These are the forefront questions of science, but they're the questions that, in one way or another, everyone asks themselves. And it seemed a lovely way to to tap into that common interest. The questions: how will the universe begin? How will it end? How did life originate? Are we alone in the universe? When I see green is the same green as you see. What's consciousness? Those fundamental questions are really the things that are driving science, and it's kind of satisfying that they are the same ones that interest people.
Yeah.
So I always, in my books, try to think of ways to get people to more interested than they are, to encourage them to ask questions, and that's really the big point. And a book about questions, which is really what this is really a book about learning, because learning should be done by asking questions.
Do you find that when you write books, it helps you clarify your own thinking?
Of course. No, it always does. I mean, that's one of the reasons I write books. That's one of the reasons why I write books. Because, well, there are two reasons. Well, three reasons. One, because I want to repay the favor. When I was younger, it was books about science that got me interested in being a scientist, and it's nice to return that favor. But also, when I write books, you could write the same book over and over again. I know a lot of people who've done that. I won't mention names.
Yeah, sure.
But in each book, I try and tackle, things I'm aware of, but try and push those my own boundaries. So it becomes a learning process for me as well. And so it's a combination. Writing a book allows me to study a topic that I might not have the discipline to study otherwise if I don't know it. And if I do think I know it, it allows me to explain it. And many, many times, as you say, I realize I understand things more than I did, or in a different context. Even like, for example, the chapter on consciousness, I had ideas about and biases about about the nature of understanding consciousness, and I found but this forced me to delve into those ideas more carefully and try and even define what consciousness was, which is not the case. Another example is the origin of life. I'd led through through the institute I ran at a university meetings a decade or two ago on the origin of life. And this allowed me to say, well, okay, I understand what those issues are, but what's been happening since then? And what are the key things that are being understood? I mean, long ago, I remember in the first book I ever wrote, which is about dark matter, I was writing about particles called axions. And I was writing about symmetries of nature. And I realized in the context of axions and these symmetries that there was an experiment that gave strong constraints on one symmetry of nature. But I realized in the process of writing it that I absolutely didn't understand it. And I thought I did. I understood what was needed to know. But when I tried to explain it, I realized, hey, there's problems. Now that I think about it, is that really right? And that happens to me in every book I write, and it's fun. It's fun, but it's also fun to learn stuff. And so they're not all books on totally new topics. So I wrote a book on the physics of climate change, which again I'd been tutored on over the years, especially as chairman of the board of sponsors of the Bulletin of the Atomic Scientists for a decade. But to go into the detailed history and understanding of climate science, that was a new area. It was also the beginning of the pandemic, so I had nothing else to do. So I was able to do it. But in this book, because it's very broad, it's really all of science, time, space, matter, life, consciousness. There are obviously areas where I knew I'd want to really read up. And again, the consciousness chapter probably
was your favorite.
Probably required the most. Well, I don't know if it's my favorite. No, it was the hardest, which is one of the reasons why I left it to the end. But it was the one where I had to read the most,
right?
Because it was an area where I had a vague understanding, and I'd run some meetings also on nature, on aspects of consciousness. But to really go into it enough to try and say what are the open questions, or to reinforce or invalidate my a priori bias that we don't understand consciousness, I had to really try and see what explanations people gave for consciousness.
Are there any interesting older sources that you looked at for any of your chapters? Let's say the life and the consciousness one.
Well, I mean, I looked at older sources. What I like about the first chapter, which is on time, is I go back to black holes, and I talk about this guy Michel, who was a unsung hero of science 100 years after Newton, who really was the first person to come up with the idea of black holes. It was fun to research his own, learn about him. There are some amazing scientists who really are unsung, and in the modern world they'd be at the very top, but they've sort of disappeared in the dustbin of history, I guess, in one way or another. And then same with with consciousness, going back to the early people who looked at consciousness. The first neuroscientists and psychologists looking at their work and seeing how much or little had changed since then. And of course, when it comes to the origin of life, that's an area where there's been a huge number of developments. The origin of life has to be distinguished, as I tried to explain in the chapter first, from the origin of the diversity of life. That's, evolution, which is, well, there are open questions with evolution. That's an area of science that's well trodden. But to go back to determine how chemistry turned into biology is right at the forefront. But we have to start thinking about the early stages of the discovery of DNA and how did such a complex molecule arise. And then it was an amazing discovery, of course, of actually an old colleague of mine when I taught at Yale. He was my dean, and I still don't have a great opinion of deans, but he was a good guy. But I never realized he was a great scientist till after he stepped down from being dean and he won the Nobel Prize and I realized his work on RNA was essential. It showed that a precursor world to a DNA world could have been an RNA world. And so it's fun to go back and see the development of ideas. And I think that's another thing about writing about science. In some ways, it's storytelling. It's not all storytelling, but I think people appreciate a story and the human interest aspect of a story. How the red herrings or how we got to where we go is something that's interesting and worthwhile talking about. We don't often always talk about it in lecture courses, but I think in books it's fun to do that.
Yeah, well, in books it seems necessary because you have to open a chapter with something that's human and relatable to the general public.
Well, I think you do, yeah.
Or statistics to the scientist. It's like, that's what we find interesting.
Well, exactly. But, people are interested in things they don't know they're interested in. And I think the key point is to convince them they're interested in things. I often tell teachers that the biggest mistake they make is assuming their students are interested in what they have to say. You have to convince them to be interested. So you have to go to where they are and try and reach out and grab them and say, this is interesting. And then people, it's like many people are afraid of science, but they don't realize they're interested in it. When you talk about warp drive or time machines, they suddenly get interested and they don't realize it's kind of forefront science.
Yeah. Tim Maudlin was saying that his favorite parts of most physics courses, most science courses in general, are the first lectures because they're selling you on the course. So he's like, when I went to quantum field theory, they told me about this is the most impactful theory in science. And then lecture 3 is on Green's functions. He's like, well, what happened to studying what is? And when you ask what is, they're like, oh, that's philosophy, actually. Don't even ask that here.
Yeah, well, I mean, there's a lot. Well, quantum field theory has certainly always been, and probably, well, I don't know if it remains, but it's always been the most challenging class to teach in graduate school or to take. And there's just a lot of stuff and a lot of intellectual baggage that you need to do. And you can't, and before you can, philosophy is useful for framing initial questions of the world, but physics has long gone beyond those initial questions so that it's driven by questions that are often quite mathematical in nature. And people don't realize that you can't just sort of start with those questions and expect to reach anything without going through the remarkable baggage that's been developed, and that has taken you far away from the questions. So, what is a fancy question, but it actually, as I talked about in Universe or Nothing, that the whole concept of something and nothing has changed dramatically because of physics, and people don't like that, but I don't care. It's the way it is. It's called learning, and we now realize, as a matter of fact, because of quantum field theory, that the difference between something and nothing is not so great as imagined before, because nothing has lots of something in it.
Yeah, let's speak about that for a moment. When I was younger, I remember questioning the universe, and I couldn't figure out how anything could come from nothing. And that was something that I had asked my brother, who was studying physics at the time. And then he mentioned quantum fluctuations, and I was 8 or so. And then it was approximately at that point that I became an arrogant and inexorable atheist.
Wow. Your brother did God's work, as we say. Go
on. I realized years later that's not an explanation to say vacuum fluctuation.
Sure. Yeah.
But I didn't know that at the time. So because I didn't know, I thought that was an explanation. However, you have now figured out some way of making that indeed an explanation. So can you cover that, please?
How you get something from nothing, you mean?
How the universe can come about from vacuum fluctuations.
Yeah, well, I can give you a summary. As I say, I wrote a whole book about it, so it's kind of... But look, the key aspect of quantum mechanics, which I do talk about in the new book, is that is that the quantum universe is many things are happening at the same time. And in particular, quantum fluctuations are happening all the time. We can't see them, but quantum systems are constantly fluctuating. And when you combine quantum mechanics and relativity, it's even more exciting because it says that empty space isn't empty. So the key thing about quantum mechanics, when you combine it with relativity, and I've described this in a number of my books, it implies that empty space isn't empty. It has no real particles, but over time scales that are so short that you can't measure them directly, and this is the uncertainty principle of quantum mechanics, things can happen that you can't see. And in particular, particles can pop into existence that weren't there before, and then pop out of existence in a time scale so short that you can't even see them. Those are called virtual particles. It may sound like counting angels on the head of a pin if you say, well, these particles are there, but you can't see them. Well, we can't see them directly, but what we can do is see their effects indirectly. We know they're there because we have an impact on the atomic energy levels of atoms. They allow us to calculate the atomic energy levels of atoms with an accuracy that's unprecedented in all of science. So we know we have to include the fact that on small scales and small times, particles are popping in and out of existence. It's quantum fluctuations in quantum fields. That's why quantum field theory is relevant. Allow you to produce particles that appear and then disappear. Fine. Well, that's for normal quantum field theory with particles and in space and time. But gravity is a theory of space and time. And so if gravity is a quantum theory, and that's a big if, we don't know for certain, but we have no reason to suspect it isn't, then the variables of that theory, space and time, become quantum mechanical variables. And then space and time can fluctuate. And you can start literally with no space, no time, and then have a little universe with space and time appear and then disappear. Virtual universes can pop in and out of existence. And in quantum gravity, that kind of phenomena happens. But it can happen that if a virtual universe pops into existence with zero total energy, then the laws of quantum mechanics and relativity say that virtual universe, in fact, can be real. It can exist for an arbitrarily long time. And then in order for it to not collapse again, if it say starts expanding and not collapses, certain processes have to happen. But if you asked, what would a universe that was almost 14 billion years old, that spontaneously arose from nothing by quantum mechanical processes, what would it look like today? And the answer is it would look just like the universe we live in. All the properties would be the properties of the universe we live in. Now, that doesn't prove that happened. Yeah. But it's strongly suggestive that possibility could explain the existence of our universe. Now, it's all possibilities right now because we don't have a quantum theory of gravity. I said if space and time, if gravity is a quantum theory, and it's a big if. We don't have a theory of quantum gravity. We may, string theory is a good candidate for that, but no one knows if it is a theory of quantum gravity in our universe. And so that's an open question at the forefront of physics, one of the known unknowns, if you wish.
And what's the name of that theory? What you just outlined, which is, okay, look, if you have fluctuating quantum fields and you were to combine general relativity, you have fluctuating space-time itself, universes can... It's just a proposal, a vague proposal, or is there a name attached to it?
No, there's no names attached to it. I propose it. Other people have proposed it, but it's just a consequence, if you wish, of having a quantum theory of gravity. And lots of people have thought about it, Hawking and Hartle, and Stephen Hawking has obviously thought about it a lot. I have, other people have. But it's right now a plausible idea, but it's not yet a complete theory because we do not have a full theory of quantum gravity.
You know that fitness coaches can be expensive. Here in Toronto, in my building, there's someone who charges almost $200 for one session. That's why I was excited when Copilot Fitness approached us. It's one of those apps that when you see how easy it is, you wonder why wasn't it invented before? And I think that's because it's more than just an app. It's this whole experience of speaking to your coach, of communicating during, after, being held accountable. Man, oh man, is it fantastic. Like, I'm someone who doesn't need motivation to work out, and I still found it helps. My wife needs motivation to work out, and I've never seen her this excited to work out before. She thinks it's because you can do this at home or the gym. They personalize it for you. There's also a streak system, which makes it such that you don't want to skip workouts. As I'm writing this, my wife said in the background, "I'm gonna beat you in it, babe." This is domestic rivalry at its finest. Changing the coach is as easy as swiping left. In person, there's always awkwardness, but it's wonderfully easy here. For me, however, I didn't have to switch, as I love my coach. His name is Rod, and Rod is rad. He took his time with me, found out what I was looking for. My wife's coach, Samantha, took the time with her. I recommend this app wholeheartedly. So are you ready to feel fit and fabulous? Give Copilot a try. It was even listed by Forbes as the top-rated personal trainer app of 2023. Head to go.mycopilot.com/toe to get your 14-day free trial with your own personal trainer. That's go.mycopilot.com/TOE for your 14-day free trial. Ever find yourself questioning reality and then you snap back to it, remembering that you have nothing planned for dinner? That's where HelloFresh comes to the rescue. They deliver pre-portioned farm-fresh ingredients and seasonal recipes right to my door. And they have over 40 choices every week, which keeps me and my wife exploring new flavors. They've got this quick and easy option that makes 15-minute meals. There's options if you're vegetarian, if you only eat fish. Something I chose, personally, was the pronto option. Their deliveries show up right on time, which isn't something I can say about other food delivery services. This punctuality is a huge deal for me and my wife. Plus, we love using HelloFresh as a way to bond. Cooking together is fun when it's all properly portioned out for you already. So are you still on the fence? Well, it's cheaper than grocery shopping and 25% less expensive than takeout. The cherry on top? Head to HelloFresh.com/50 Theories of Everything and use the code 50 Theories of Everything to get 16 free meals plus free shipping. That's 16 free meals, people. Don't forget, HelloFresh is America's #1 meal kit. Links in the description. In the limited time that I have to speak with you, I want to ask you a bit about Dyson, your conversations with Dyson, which you talked about. Dyson was thinking extremely theoretically, like, what could it be? What could it be? Not just for us to live forever, but for a possible being to live forever. What would that mean? Is it possible? And he came up with a solution that has to do with, well, if a conscious being had an infinite amount of cycles, that's akin to it living forever. Now, I don't know if he has to assume a continuous amount that you can divide space or that you can divide time to, but regardless, you'll speak about that.
You know, he came up with very interesting proposals for how a hypothetical species could do that. We had wonderful debates.
Yeah, please outline that, and then please outline what your objections were and what that looked like with him retorting and what were his retorts.
It was fun. It was, you know, those kind of conversations are fun in science, going back and forth. Well, look, he had argued in a typical Dysonian way, which says, forget what's practical, but in principle, is it possible for a civilization to live forever? Yes, I'll define it as if it has an infinite number of thoughts. If it has an infinite number of thoughts, then that civilization has survived forever. And then he said, well, how could you have an infinite number of thoughts? Because, you think when we're thinking, it takes energy, 10 to 20 watts in our brain, which is not a lot, but enough. So clearly, you'd think it would take an infinite amount of energy to have an infinite number of thoughts. But if we only have access to a finite amount of energy, then we can't do that. But then he pointed out that if you can have infinite series that converge to a finite number. The Greeks discovered that. And Zeno's paradox, for those who know of it, or at least we now know a solution to Zeno's paradox. I'm not sure the Greeks exactly figured it out. But in any case, and so he argued that one way to have an infinite number of thoughts would basically be wake up, have a thought, then go to sleep, where you're not using any energy, basically, if you could imagine such a thing, and then wake up a little bit longer later and have a thought, and then sleep longer and sleep a greater.
It sounds like the ideal life.
Yeah, exactly. At a greater and greater fraction of the age of the universe, you sleep each time, so you're sleeping for longer periods, and during that time, each time you think, you use less energy, and anyway, he showed you could, accessing finite energy, have an infinite number of thoughts, and that sounds good. The problem is,
briefly, before we get to the problem, why is that so remarkable? Because like you mentioned, we've known about infinite series that converge for quite some time now. So why did it take Dyson to come up with that? What did he contribute to it that was different, that was subtle?
Well, I think his realization that you see, the point is that because we think in terms of metabolism, the standard wisdom was that a non-zero metabolism will therefore require infinite energy access over infinite time in order to continue, because it's always. And I think the cuteness of his example was imagining a system that could basically turn itself off, and really have a life that's, many people would not say, well, if you get old, it sounds nice, but a life where you're sleeping more and more and more and more, which most people don't think of as a vital civilization. So I think it was his recognition that in an expanding universe, you have to do the equations right. The free energy that you use, the integral of that could be finite, even though there are an infinite number of wake up periods. It wasn't at all obvious that you could get it to converge. And so I think it was a combination of that and realizing that, if there's such a system could turn itself off, then you could in principle do that. But the problem, there's lots of problems there. Immediately quantum mechanics comes into a problem, because quantum fluctuations are such, it's kind of hard for a system to use zero energy at all.
Yeah.
But also, how do you wake up? It was one example. I mean, so you want to wake up, but then you have to have an alarm clock. Well, how do you have an alarm clock that has an infinite number of wake ups that uses less energy? And then we showed them, hey, the alarm clock is going to use an infinite amount of energy. They said no. He came up with an orbiting planet scheme, which was really tricky for orbiting planets that eventually, or not planets, but orbiting particles. When they collide, the alarm clock goes off, and it doesn't take any energy to orbit a planet. And then we point out eventually the laws of quantum mechanics will get you there as well, because the uncertainty principle means you can't, at some very basic level, you can't fix exactly the momentum of two particles, and eventually, you can't fix it well enough. You can fix it to some certain level of accuracy, but if you want them to orbit each other for 10 trillion years before they collide, then the uncertainty in their momentum is such that every now and then they're going to miss each other, and you'll sleep forever. And there are little things like that. And anyway, and then his final argument was a black cloud, like that of the black cloud of what's his name, the father of the Big Bang. Well, sort of the
well, some conscious being that doesn't resemble.
No, but the black cloud, it's a great story. It's probably the best science fiction story ever written. It involved a discovery of a cloud, and it was realized that the motion of the particles in the cloud encoded intelligence, and he argued that cloud could slowly expand, and you could imagine it would live forever. But in fact, ultimately, and we went back and forth, but ultimately, and this was before we knew, we were having that debate before we knew that the expansion of the universe was speeding up, something I actually proposed a few years later, and then it was discovered to be true. But we both recognize that if the expansion of the universe was speeding up, then his arguments about would fall by the wayside. There's no way life can exist forever in a universe that's accelerating like we have. And so it was even though we agreed to disagree about what happened in other cases, we agreed about that case. And since that appears to be the case for our universe, it looks like it's good news for the future, long-term future of life. As I like to say, the future is miserable, but it's going to be a while before it's going to get too miserable. Trillions of years.
And with Dyson, I sent a YouTube video. It's been a while since I've seen it, but he was saying that gravitons aren't detectable. He had some
Oh yeah. No. In fact, actually, he said that, and then I actually was at a meeting with him when he argued that he gave a great argument for how all the experiments that you could detect a graviton directly wouldn't work. And I'm not sure all of his arguments are exactly right, but it was a brilliant, like typical Dysonian paper. It was, what could you do in principle to do this, and in every case showing a real trick for why it wouldn't work. But in fact, what I talked at that meeting, and he agreed with me ultimately, but I showed him that no experiment we can do on Earth will detect gravitons, but the universe as an experiment can detect gravitons, because the universe can do things we can't do, like ultimately have regions that are expanding faster than light away from each other. And I showed him that this process of inflation in the early universe would produce gravitational waves, but only, which we can measure today, but only if gravity was a quantum theory, in which case there would be gravitons.
Mm-hmm.
So the universe could be if we detect gravitational waves from the expanding universe, which we haven't done yet, we've just detected gravitational waves from black holes that are colliding, but we haven't detected gravitational waves from the Big Bang, or this period called inflation. If we could do that, those gravitational waves would be generated if and only if, at a very fundamental scales, gravitons were being created and destroyed. And so we could use the universe as a way to prove that gravity is a quantum theory. If we were able to detect gravitational waves from inflation, it would imply that gravitons exist. And so it'd be an indirect way. You wouldn't directly detect them, but the universe, in that sense, would be a graviton detector. You'd see, just like when a Geiger counter detects a radioactive decay, but I don't see the radioactive decay, what I hear is a click that's been turned into a classical thing I can hear. Well, in some sense, gravitational waves from the early universe would be like the click of the Geiger counter. If I saw them, it would be the classical manifestation of a quantum phenomena that happened at the beginning of time.
You also mentioned in your book about inflation that there are various inflationary models, and that some of them can be used to indirectly have evidence for multiverses. Okay, so let's explain that. What's meant by that there are various models? Because the way that it's told to the public is like, oh, well, the universe expanded. Okay, so it's as if there's one inflation theory.
Well, there's an idea. Inflation is an idea more than a theory. You can show that under certain conditions, the universe will expand very fast at early times. It's almost generic. The hard part is to get it to stop from expanding very fast, because if it didn't stop expanding very fast, life couldn't form. Exactly how you do that is the context to a model. So you embed that idea in a mathematical model of how the universe is evolving. And there are different models, and none of them are very pretty, to tell you the truth right now. I suspect there's things we're missing. But almost all of those models for how you stop expanding very, very fast imply that there are actually other universes, because what really happens is there doesn't seem to be any way to globally stop the universe from expanding very fast. But what you have are sort of like little drops or snowflakes. You have the background universe is expanding very, very fast, but within a small region, there's a phase transition, like a snowflake forming or a raindrop forming out of vapor. And in that region, you decouple from that background fast expansion, and you have a hot Big Bang. Okay, but that means most of the rest of this space is still expanding. It's somewhere else. You decouple and have a hot Big Bang. But it turns out you can decouple from that expansion. You can have a phase transition in many different ways, just like you can create snowflakes that have many different shapes, right? And each different way you decouple from that background expansion can result in different laws of physics. And so what inflation generically says is, yes, we can understand how our universe came to be as one of these sort of drops inside a rapidly expanding universe. But generally, if that's true, there are other universes out there that could be quite different that we'll never know about, because the space between us and them is expanding so fast we'll never know about it. That's the multiverse. And moreover, since it goes on infinitely long, you'll eventually create an infinite number of such other universes. Okay? Yeah. Now, we'll never detect those other universes. So people say that's kind of science fiction or religion or something. But if we could detect, say, gravitational waves from inflation, then we'd be able to probe the exact model of inflation, the characteristic of how we decoupled from that background expansion, and we'd be able to tell which model, if any, of inflation was right, and probe its theories. And once we did that, we'd know if that model predicted a multiverse. So we'd know indirectly that there are other universes, because we'd probe the model and say, yeah, that's what happened. But if that happened, there have to be other universes out there. So it's an indirect detection, just the way in 1905 we knew atoms existed, but there's no one ever figured there'd be a way to see them directly. We always detected their effects indirectly. We can now more or less see them with fancy kinds of electron microscopes and other things. But all the evidence for atoms, we believed atoms existed shortly after 1905, because it explained everything we saw, even though we never thought we'd see one directly. And that's the way it'll be with a multiverse. We'll never detect those other universes. But if we have a theory and we can test it very, very well, let's say we had a theory of inflation that we could test very well, then and it made 50 predictions, and you tested all those 50 predictions and they were correct. Well, the 51st prediction that you couldn't test, you'd have strong reason to indirectly believe was correct.
And are we currently looking for these primordial gravitational waves?
Yes, well, we're looking in different ways. Yeah, we thought we had discovered them 10 years ago, or maybe 8 years ago, 10 years ago, close to. We're looking at ripples in the cosmic microwave background radiation, the radiation from the Big Bang. These gravitational waves would leave a signature that's very hard to detect. And then I think it was 2015 or somewhere around then, maybe a little later, a group of experimentalists thought they detected. In fact, it was kind of sad because they detected precisely what they thought the signal of such primordial gravitational waves would be, with an amount as large as was allowed by other constraints. But it turned out that they were fooled. Turned out that dust in our galaxy produced the signal that they thought they saw. It doesn't mean that, what it did. Right. I shouldn't say it that way. It turns out that dust in our galaxy could produce a signal that was as large as what they saw. It doesn't mean that there wasn't a real signal embedded in that, but because extraordinary claims require extraordinary evidence, the simplest thing to assume is that, well, what you can say is you cannot distinguish it from dust in our galaxy. So more refined experiments are going on in the South Pole and also in South America and in high levels, building these probes of the cosmic microwave background radiation that are looking for this primordial gravitational wave signal. It may not be there at a level that they can see. We don't know. But there are ongoing experiments looking for it.
What you referenced was Brian Keating's work?
Yeah. I mean, Brian Keating was part of that first experiment that thought they'd seen those gravitational waves. He wasn't the PI on it, but he was working on it. Yeah, and he's working on the subsequent experiments that are trying to refine the measurement. Maybe they'll see it, maybe they won't.
So neutrinos are your favorite particles.
That's true.
Yes.
Yep.
And then there's something called CP violation, and there's something called leptogenesis. And neutrinos, CP violation.
Yeah, wow. It's going to be this.
Please integrate them all.
We're getting quite technical. Okay, you read the book for sure.
I'm a math and physics grad from U of T, and the audience tends to be graduate students in physics, math, consciousness, computer science, as well as researchers.
Neutrinos are my favorite particles because they're most elusive particles. And it turns out they may be my favorite particles for another reason. They could be responsible for our existence. Because one of the big problems, the problems that got me into cosmology and many other people, the first time particle physics was really applied to cosmology was in the 70s or so, when one of the big problems is, why do we live in a universe of matter? It may not sound like a problem, but it is if you think about it, because matter and antimatter are largely indistinguishable. And if you have a hot Big Bang, you'd think you'd create as much antimatter as matter. And if you did, then the matter and antimatter would annihilate. You wouldn't have anything left over. So there had to have been a slight excess of matter over antimatter early on. How was that created? We still don't know the answer, but we have ideas for how it might happen. But there are problems with all those ideas. If you create just these particles called baryons, which are like protons and neutrons, and you make a slight excess of them, then it turns out there are later things that can happen in the universe that will erase that excess, or you require a theory that has parameters that we've already ruled out. What you're required, and Andrei Sakharov, who later won the Nobel Peace Prize, was a brilliant Russian physicist, the father of their atomic bomb, who in 1967 gave 3 conditions that are required to have more matter than antimatter. You have to have a departure from thermal equilibrium. You have to have, the theory has to allow you to violate what's called baryon number, baryons and antibaryons, so you distinguish protons from antiprotons. It also has to have what's called CP violation, or time reversal invariance violation. So that it has to violate, matter and antimatter have to be different in a fundamental way, a very small way, but different. So you have baryon number violation, but also matter and antimatter can't be quite the same. They have to have some different interactions. And he showed that if those 3 things were true, if you had a theory that those 3 things were true, then you could generate an asymmetry in the early universe that would produce more matter than antimatter. The problem was in 1967, none of those things were true. The standard model at the time didn't have baryon number violation. There was no evidence of any need for out of equilibrium processes in the early universe. And it certainly didn't have CP violation. Well, CP violation had just been discovered in 1965. And of course, since then, our theories of going beyond the standard model include all of those things. The grand unified theories have baryon number violation almost automatically. Maybe they have CP violation. But it turns out it's hard to make them work. But what has been recognized is, well, the neutrino sector is largely unconstrained. Because, we've measured CP violation in the observed sector of the rest of particles. But because neutrinos are so elusive, it's been very hard to do experiments on them. Mm-hmm. And it's quite possible, especially if neutrinos are their own antiparticles, then that violates something called lepton number. An electron has lepton number 1, an anti-electron has lepton number -1. But it turns out, well, if neutrinos are their own antiparticles, and if they have a mass, I should say that, and if they have a mass, that mass will that will require you to violate lepton number. Namely, you could create 2 neutrinos out of nothing. Okay, and instead of a neutrino and an antineutrino, because an antineutrino and neutrino are the same thing, right? So the lepton sector via neutrinos is very unconstrained, and it's been realized that maybe if there's CP violation in the neutrino sector, if not only are neutrinos or antiparticles, but there's CP violation, then you could have a process in the early universe that's now unconstrained by experiments that would, if you wish, would produce more neutrinos and antineutrinos. Okay? But in order for that to happen, you probably have to have extra kinds of neutrinos, and that we can't see right now. Oh. And if that happened, then basically those interactions and the decays of those particles would be fed into the visible sector and end up producing more electrons and anti-electrons and more protons and antiprotons. So basically, you'd produce the asymmetry between particles and antiparticles in the neutrino sector, and that would feed down and eventually give us more matter than antimatter. It's called leptogenesis. And right now, many people think that might be the most attractive possibility for how we end up getting more matter than antimatter in the universe.
2 questions. Is there a consensus right now to whether neutrinos have mass? And then
neutrinos have mass because, they've been measured to oscillate between, electron neutrinos, muon neutrinos, and tau neutrinos oscillate into one another in a way that wouldn't be produce measurable effects if they didn't have mass. We don't know. Their mass has to be very small, and we haven't measured their mass directly. And we don't know exactly which particle's heavier. All of those things are open questions. But we do know that neutrinos have mass. So that's already and in fact, in the standard model, that's not really an easy thing to put in. So already that's indications that there's physics beyond the standard model. So that's another thing that's great about neutrinos, because they're pointing us in the direction of sort of beyond the standard model of particle physics.
So the inconsensus is what mechanism? Is it the seesaw mechanism, or is it something else? Like, we know it has mass, it's just what produces it.
Yeah, we just don't know. I wouldn't call it lack of consensus. I just say we don't know. But you're right. There's a lot of, it's the same thing, I guess. There's a lot of ideas, and a lot of ideas for where neutrinos get their mass and what their masses might be. But right now, we don't even have the experimental data to be able to distinguish between them. And we're building experiments. Like, there's a long baseline experiment in Fermilab that's going to shoot neutrinos to a detector in South Dakota, in the Homestake mine, and it will be designed to try and look and measure the properties of neutrinos and masses and see if we can answer these questions. Measure CP violation, among other things.
Yeah, and if I heard correctly, I believe you said that in order for leptogenesis to occur, there has to be other kinds of neutrinos that we don't currently observe. And are you referring to right-handed, or are you referring to like new generations?
I'm referring to right-handed neutrinos. Yeah, heavier right-handed neutrinos. Generally, that's the case. Yeah, and then those could feed down into normal because they're unstable, and they'll decay and produce normal matter, etc.
As far as I recall, neutrinos propagate as mass eigenstates, but they're detected as flavor eigenstates.
That's the reason. Yes, but that's the reason they oscillate, because the mass eigenstates are not the weak eigenstates, if you want. And so the particle that's propagating is not an eigenstate of label electron, muon, or tau.
Yeah.
And so the massive particle that propagates, but it periodically looks more like an electron neutrino, and then at other times like a tau neutrino or whatever, or muon neutrino.
Would an analogy for the audience be like, you don't know if it's spin up or spin down, you measure it and then it becomes one? Or no, is that a poor analogy?
Well, it is that if you want to think of it, it's not a bad analogy. It turns out the weak eigenstate, the thing we label as an electron neutrino, is a superposition of mass eigenstates. So it's like saying that a particle that's in that spin half is in a superposition of spin up and spin down, or spin up and spin sideways, or whatever you want to call it. So it's in a quantum superposition of two different states. And sometimes you measure, and it's fine to say that. Sometimes you measure it, and you measure, it's like if you're in a superposition of a spin up and spin down, if the particle's oscillating, let's say, in a magnetic field. Sometimes you'll measure it spin sideways, and sometimes you'll measure it spin up. And this is somewhat similar to that. Sometimes as the particle's propagating, you'll measure it and you say, oh, it's an electron neutrino. And other times you'll measure it and say, no, it's a muon neutrino. So it's not that bad an analogy. It's the same. It's saying that because the mass eigenstates aren't the weak eigenstates, another way of saying that is the weak eigenstates, the flavor eigenstates, are linear superpositions of the mass eigenstates, but that also implies that the mass eigenstates are linear superpositions of the flavor eigenstates.
So it's not like you can say, okay, well, which one is more fundamental? It's like you can draw your bases in any way. So is the flavor...
energy is fundamental in terms of propagating in space and time, energy and momentum. So they determine the states that propagate. The mass eigenstates are the ones that propagate.
Sorry if this is a foolish question. I just don't know.
No. So, but the point is, it's kind of, it would be arbitrary if it weren't for the fact that we measure that the rest of the particles, the other particles we measure, like electrons and muons and stuff, that their mass eigenstates are weak eigenstates. And so that they're good labels for all the other particles that we measure, the ones that make us up, electrons and protons. They're labels because they have electric charge. Those are good labels, but the neutrino is neutral, and so the label we give it is somewhat arbitrary for it.
Okay. Now you have studied dark energy and dark matter plenty. So there's some people that say, well, it's not matter; it's a modified gravity. What do you make of that? There's also something called teleparallel gravities.
Well, there's lots of ideas. I don't know. Every week there's a new proposal. The simplest proposal is that it's the energy of empty space.
Oh, for dark energy. What about for dark matter?
Dark matter, it's not anywhere near as exotic. It's just a new kind of elementary particle, and the standard model, and every theory that goes beyond the standard model predicts a host of such particles, whether they're WIMPs or supersymmetric particles or axions. You can't create a model that goes beyond the standard model. Well, maybe you could, but it's very hard to do without dark matter candidates. So that's not it's, as my friend Frank Wilczek used to say, it's the most radically conservative assumption. Which is what you do in physics, right? It's much more conservative to say there's a new kind of elementary particle, since we expect there will be, than to say that gravity, if one of the fundamental forces in nature, somehow gets modified in exactly the right way on the scale of galaxies to produce the weird effects that we see. That's why I find dark matter, the particle explanation for dark matter, to be far more compelling theoretically and observationally than anything else.
Okay, now let's talk about infinities briefly. So there's this phrase that renormalization is a dippy process from Feynman. And then there's...
Yeah, well, Feynman really didn't understand it. He won the Nobel Prize for it, but he never really understood it.
So since the 70s, there's like the Wilson group, which says that it's a reflection of our nescience, like our ignorance about the fundamental laws. But still to this day, some people think of renormalization, even some physicists. I was speaking to one off air, and he said, no, it's still sweeping infinities under the rug. So what is your view?
No. Look, my view is that the mistake of thinking of infinities is the mistake of thinking that any theory is good at all scales. We used to think of like electromagnetism as a theory of nature, and it's true for all scales, but it's not true for all scales. We know, in fact, at a small enough scale, electromagnetism unifies with the weak interaction. So if you take your theories and you do your integrals up to infinity, you're assuming the theory works at a scale where it may not work. So it's making vast assumptions about what happens at scales you can't measure. It turns out that the sensible theories that we can measure at low energies are ones that are insensitive to the new physics that is inevitably going to happen at those high scales. And renormalization is just a way of separating out what we can measure and know from the physics that is irrelevant at low scales. It's relevant, but it's suppressed by powers of very large masses. Any new physics that comes in has an effect that goes like 1 over m, the mass scale at which it comes in. And so renormalization is just a way of basically systematically separating out those higher order effects that are irrelevant. And if there are no theories, you can take that mass to infinity. Mm-hmm. And renormalizable theories are theories that make sense if you take that mass to infinity, if you take the scale of any new physics to infinity. Mm-hmm. If they were sensitive to high energy physics scales, then they wouldn't be renormalizable, but then they wouldn't be the theories we see anyway, because it would depend on new effects. So it's nothing, the whole notion of associating with infinities is just because we don't know what the physics is. So we say, well, if it were infinitely big, how can we dissociate that from the level of the physics we measure? But it's really just equivalent to the statement, and this is Wilson's recognition, that those new theories at very high scales are irrelevant to understanding the physics at scales we see, but the theories evolve with scale, and eventually that high scale physics will be important. And in fact, the physics that some of the physics you can't always see will change the way in which those theories change with scale. Yeah. In fact, one of the ways we look for new physics at the Large Hadron Collider is to look to see if the strength of the weak and electromagnetic forces are scaling as you think they would. If they're not, then it may imply new virtual heavy particles that are contributing to the way those forces are behaving, and it would be a signature of new physics. So it's not a matter of sweeping infinities under the rug. It is if you do the mathematics, but physically, what you're just saying is, I don't know what the new physics is, and I'm going to isolate that physics that I don't know, and define a theory that works that's defined and works at this scale and gives all the relevant answers at this scale. At another scale, the theory may change. So we really realize there are no fundamental theories in nature. All physical theories evolve. That is, unless you get to string theory, and then people have argued that then that evolution disappears and you have truly a theory that's true at all scales. But we don't know if that's the case or not.
Don't want to keep you for too much longer, as there's a hurricane that's impending, and I would like to speak to you again.
Yeah, we could. This is certainly a fun and detailed conversation that's more detailed than I usually get to do online.
Yeah. So you mentioned that the Higgs field is like a Bose-Einstein condensate. Now, I don't know if you meant that poetically or literally.
No, it is a condensate. So as you know, and maybe your listeners know, that no two fermions can exist in the same state, but you have bosons, particles with zero spin or spin 1, they can condense. They all want to be in the same state. And when they're in the same state coherently, it looks like a classical field. That's why we can measure electric fields, because photons can exist coherently in the same state. Mm-hmm. Enough of them, enough quantum particles add up so the effect looks classical. Well, the Higgs field is a condensate of particles, of Higgs particles.
Yes,
and that exists in empty space. It's like a background field. It's like a background electric field. Mm-hmm. It's just we don't measure it as an electric field. We can't measure it directly, but the way we can measure it is by hitting it really hard with particles, and then we knock other particles out, and that's basically what we do at the Large Hadron Collider. And so the Higgs field is really a Bose condensate of particles, a Bose-Einstein condensate of particles. It's a background field that's made of a coherent superposition of many, many quanta of the Higgs field, which are Higgs particles.
Well, Professor, you got to get going, and I could speak to you for another 3 hours, maybe longer.
Maybe we'll speak again.
Yeah, I would love to. And so why don't you tell the audience, what are you working on next? Are you writing another book?
I am probably writing another book. I just finished some work on ways to maybe test ideas of quantum gravity in the laboratory by using fluids. So we have a paper that just came out in physics, in Nature Physics, that's not yet appeared in print, but it's just been accepted and appeared online.
Oh, congratulations.
Thank you. But I'm writing a new book, but it's probably not going to be a science book of the type that you're used to. There's a number of possibilities.
The fiction?
Well, fiction is one of the possibilities. Probably not for this book, but there will be a fiction book coming out. This book will either be. I've started because enough people have asked me to write a scientific memoir. So I've started it. We'll see how long my patience lasts. Because I've known many interesting scientists and other people over the years, and my own experience as a scientist. Some people think it's worth writing about. We'll see. I had my arm twisted, but we'll see.
For those who are watching, I'm holding up the book called The Edge of Knowledge. That's Lawrence Krauss's recent book. Actually, this year, a couple months ago,
it came out. Yeah, just came out in May in the US. That's right.
The link to that will be in the description. Thank you so much for spending your time with me during this tumultuous weather.
Hopefully, it'll all be much ado about nothing. And since I'm a big fan of nothing, I'm going to hope for that. Okay. Take care.
Take care.
Bye-bye. Bye-bye.
If you have questions for Lawrence Krauss, then leave them below in the format query by writing the word query with a colon and then your question. The podcast is now concluded. Thank you for watching. If you haven't subscribed or clicked that like button, now would be a great time to do so, as each subscribe and like helps YouTube push this content to more people. You should also know that there's a remarkably active Discord and subreddit for Theories of Everything, where people explicate toes, disagree respectfully about theories, and build as a community our own toes. Links to both are in the description. Also, I recently found out that external links count plenty toward the algorithm, which means that when you share on Twitter, on Facebook, on Reddit, etc., it shows YouTube that people are talking about this outside of YouTube, which in turn greatly aids the distribution on YouTube as well. Last but not least, you should know that this podcast is on iTunes, it's on Spotify, it's on every one of the audio platforms. Just type in Theories of Everything and you'll find it. Often I gain from rewatching lectures and podcasts, and I read that in the comments, hey, Toe listeners also gain from replaying. So how about instead re-listening on those platforms? iTunes, Spotify, Google Podcasts, whichever podcast catcher you use. If you'd like to support more conversations like this, then do consider visiting patreon.com/KurtJaimungal and donating with whatever you like. Again, it's support from the sponsors and you that allow me to work on Toe full-time. You get early access to ad-free audio episodes there as well. For instance, this episode was released a few days earlier. Every dollar helps far more than you think. Either way, your viewership is generosity enough.